Yeah. So it's our pleasure to have Professor Tamal Day here today. Currently from Purdue, but formerly from Ohio State. Professor Day has many honors and over his time. I'll mention a few. So he has co-authored 2 books, Curve and Surface Reconstruction, that was published by Cambridge University Press, and then Delineate Mesh Generation, that was published by CRC Press. Over his career, he has co-authored more than 200 scientific articles. He is a fellow of IEEE and a fellow of ACM. He has also been inducted as a fellow by Solid Modeling Association. He is currently at Purdue, but he was previously at Ohio State, where he served as the interim chair of the Department of Computer Science and Engineering for a couple of years. So with that, it's a pleasure having you here, and glad you could make the time to give this talk to us.
Thank you, Ridesh. Actually, it's my pleasure to be here, and I thank both Ridesh and Iowa State for inviting me to give this lecture. So today, I thought I'll talk about this particular topic of computational topology and data analysis, a new way of looking at data. Let me just tell you a little bit of personal history on this. When I was doing my postdoc with Herbert Ellsberner at UIUC in 1991-92, that's the first time actually we started looking into topology, particularly the computational aspect. We are working on computational geometry, and that time we just said, okay, let's look at computational topology. And Herbert will tell me to read this Munkres book. Those of who know about this is the introductory algebraic topology book. And that time I didn't have the mathematical background as much needed to understand it, but we started reading it, and then we realized actually that how important the topology will be, and that part was a little bit missing from computational geometry, and that's why we wrote in 1999, we said that there should be a field called computational topology. There is a survey by Herbert, myself, and one of our other co-authors, Guha. So, and then after that, the area has flourished, and then came persistent homology. Herbert came up with this idea, and then the mathematicians joined, and Carlson and others joined, and then the area has flourished. But I take a little bit of pride that at least we started it very early, before the mathematicians actually came in to say that this topology is important. So you can see in computational geometry already we had papers called in the subject of computational topology in early 90s. And I thought, since it has developed lately so much, with a tremendous job from computer scientists and mathematicians and also statisticians, I thought this is one thing to tell, that there is a way of looking at data a little bit different from the traditional way we look at data through machine learning neural network. And it's not possible for me to give the entire scope or entire gamut of this field, topological data analysis. I'll be on very high level. So those who are familiar with mathematics, they will be probably very bored. But I will try to cater to people who are not that much familiar with topology and particularly homology. Okay, with that, let me start with my very short introduction to what is topology. A topology probably the best way to visualize it is, you can see it's like a subset of a plane or some subset of a 3 dimensions. Actually, the definition is much more integrated than that. It's a set of open sets defined by open sets and satisfying certain conditions. But the main point is that these topological spaces by themselves are not by themselves, they do not bring anything new, but the main point is the maps between them really make things much more useful. One of the map is called the homeomorphism. What does that mean? It means that two spaces T1, T2 are homeomorphic if they're topologically equivalent. And again, I'm hand waving here. What do we mean by topological equivalent? So by picture, for example, here on the torus, on the left hand side, this torus, can you see my cursor? If I can, somebody tell me whether you are seeing the cursor?
Yes, we can see it.
Oh, thank you. Okay, so there is a torus here, and this torus is topologically equivalent to this here. And this is a knotted torus. This is also equivalent topologically to another knotted torus, but this time this embedding is different because the knot is inside. So topology does not, the homeomorphism doesn't care about the embedding. But it tells you that all these three spaces intrinsically connected very similar. So this topology actually brings out what is called the connectivity within the space. OL, so that is homeomorphism. And there are other maps, homotopy equivalence and isotopy. Isotopy is a stronger notion of homeomorphism. These spaces are not isotopically embedded, but they are homeomorphic. Isotopy embedding will say that actually you cannot knot things here. Okay, so with this, let me tell you how I was brought into topology. What was the thing which motivated at least me to come into topology? And actually,
Professor Dev?
Yes.
Sorry, is it okay if I ask a question, basic one? I am not familiar with topology.
Okay, sure.
In this torus example, it's interesting. So the left side is basically a donut, right? It's a
Right.
hole in the middle.
Right.
And the knot, which is the middle one, is like I can flatten it out and it'll cross itself, right?
Yeah, but you don't look into what happens in the middle. You just look into the final embedding. So this as a space is equivalent to this. Don't see what happens that how do you bring this left torus to this? That's a different question. That's the question of isotopy actually.
I see. Okay, thank you.
So, these two, I'll just put two applications, surface reconstruction and mesh generation, which motivated me. And actually this motivated the a lot of computational geometers to look into this topological data analysis. In a sense, actually, the persistent homology came into being from this applications. I know about this history because Herbert was working on something on this reconstruction, and that led to him to invent persistent homology. So what is a surface reconstruction problem? He says it is the problem of, suppose you have been given a set of point cloud data, like here, these are all points in 3 dimensions, and we do not know where the points are coming from. It's just XYZ coordinate. The problem is to connect the points with the triangulation like here, so that we recreate the space. And this triangulation, that is the problem of surface reconstruction. So when I showed this problem to my kids, they said, okay, Dad, you do these things, these triangles are so easy, means you just connect the points. You see, it's very, very easy to propose the problem, but really solving it automatically through algorithm without any hitch is something else. So the problem of reconstruction is to compute a triangulation from a given point cloud data when you don't know where this point cloud is sampled from. Well, so then definitely there is a need to concretize the notion of when you say a sample is good. Because, for example, for a face, if I just give you 4 points on the head, chin, and on the mouth, you cannot reconstruct the surface if you don't have enough sample. So then there should be a notion, or it demands a notion of what we call something dense enough. For this, let me introduce what is called the local feature size. So what is the local feature size? So for example, I'm showing here a curve. That's your space, for example, you think about it. And then the medial axis of this curve is something which is exactly at the middle. Again, I'm not giving you the definition of the medial axis. It is the locus of all the maximally empty balls. So these are the centers of maximally empty balls. This is the medial axis. And local feature size at any point x is the distance from x to the medial axis. In a sense, actually, this captures how complicated locally a shape is around the point x. So this is a qualitative, not quantitative measure of how complicated x is through this local feature size at x. And we say x has a sample point, like say x is this point, and there is a sample point. It has a sample point with epsilon times local feature size x. If it has a sample point within epsilon distance, if its distance is epsilon times the local feature size at the point x from x. Okay, and then in 1999, actually around 1998, 99, Aminta Byrne came up with this very nice algorithm on reconstruction where there could be some guarantee. Guarantee is the following. Suppose you have a epsilon sample. So epsilon is capturing actually the density. The smaller the epsilon is, you can think about the definition, the higher the density is. So then one can prove theorem like this. If there is a epsilon sample from some manifold, which I'm calling it, which is denoting it as sigma, such that any point x has a point in your reconstruction with this distance. So this algorithm called Crust will reconstruct a piecewise linear surface, a triangulation from a point cloud data, and it is giving this guarantee that if the point cloud is epsilon sample dense, or if it is an epsilon sample, then the output, every point on the sample manifold has a point within a small distance of the output, and conversely, every point on the output has a point on the manifold. So this is giving you a geometric condition. So that means it is telling you that the output is not very far away from your input in terms of geometry, some kind of distance with respect to the local feature size. You can, one good thing about it, this is scale invariant. I'm not talking about any particular scale. This algorithm is scale insensitive, which is very, very important for applications. But this theorem lacks the topology here, because, for example, if I give you a circle, you can definitely produce something very nearby the circle, but you cannot say that whatever you have produced is also something like a circle. It can be a zigzag or a bunch of edges just near the circle. That will satisfy this geometric condition, but it will not satisfy the topology condition. So then we came up with this new algorithm in 2000, actually, four of us, and we called it the Cocone algorithm, and which guarantees the topology now. It says this algorithm will also have the geometric guarantee, but whatever surface we produce is homeomorphic to the sample surface. So you need the topology here. So that this is just to motivate where topology is very important for giving guarantees. So here is an algorithm which can guarantee both geometry and topology. So again, I'm just telling you already, this has pointed out, I worked on this surface reconstruction for a long time, and then wrote a book on this with different algorithms. But then the question definitely comes, the open questions came, what happens for the point samples in high dimensions? What guarantee can you do? And there have been quite a few work on that since then. Okay, and then the second problem, which also motivated me to look into topology, is called the problem of mesh generation. So, what is the problem? Is the other side of the coin. Surface reconstruction, you are given a set of sample points, not the surface. Then you are asked to recreate the surface. In the mesh generation, you are given the surface, and then you are asked to sample and connect those samples, the mesh. Okay, so here I'm showing a surface mesh for some piecewise smooth surface. Here is also, one can say, not only surface mesh, the volume mesh. In volume mesh, you would not only look for triangles, but also in the triangulate the interior with tetrahedra. So again, there was several algorithms which could do some geometry guarantee, but then you realize that you need the topological guarantee, and we came up with a topological guaranteed algorithm, which I have put it in my book. And the algorithm says the following: means I'll just tell you what the guarantees are, just to highlight where topology comes into picture. We guarantee first. Suppose the given surface. Okay, whenever I say two manifold, two means two-dimensional manifold. Two-dimensional manifolds are surfaces. Okay, so we guarantee that the output surface mesh is always a two-dimensional surface. Okay, it definitely says piecewise smooth surface or piecewise linear surface because it's made out of triangles. But you guarantee first it is a two manifold. See, this is a concept from topology. And then we guarantee the following, that there is a parameter with which the algorithm works, which we call the lambda, which will determine that how dense your output mesh is, or how good the output mesh is. We say that the output mesh is related to your input surface sigma by isotopy. Again, isotopy, that's what someone asked me the question. Here exactly, you can now show that the input surface can be continuously deformed to the output surface without those crossings or anything, and that is now guaranteed by isotopy. See, here again topology comes into picture. Okay, and then of course this second condition is the geometric condition and the normal condition. These are all geometric condition. But my point is, you need also this topology condition here. Okay, this is the geometric condition, Hausdorff distance. But anyway, so I just wanted to tell you again, this is the work before I came into topological data analysis all the way. I worked into these two areas where we realized, at least I realized, that topology will be very important. Okay, now let me jump into this topological data analysis, which I wanted to talk about the rest of my time. Okay, so what is a topological data analysis? Maybe some of you already, okay, I don't know why it is here. Okay, so here is a cartoon picture of what is a topological data analysis. I'll come back to this picture later. Okay, so again, this topological data analysis is built mainly on this homologic groups or homological algebra, and it's not possible for me to teach within these few minutes what is homology. It's very difficult to even build the intuition, but let me just point out certain things very briefly. What does it capture? A p-dimensional homology actually captures p-dimensional cycles in a space up to boundary. Okay, what does it mean? It's mouthful. So p-dimensional cycles, okay, let me say what is one-dimensional cycle. One-dimensional cycles we all know. In the graphs, we know the cycles. Those are one-dimensional cycles. Like here, I'm showing so if you look into this graph, all these edges and vertices, there are many one-dimensional cycles. These are the one-dimensional cycles. Okay, but I also want to point out that in this picture, there are something called triangles. Like this is a triangle, and this triangle is filled. But here, this triangle is not filled. So this triangle is absent from this space. This triangle is present. This triangle is present. And this is called something called simplicial complex. So I'm talking about the homology of a simplicial, homology group in of a simplicial complex or simplicial homology. What it captures again, it will capture this cycle up to boundary. What does it mean? This cycle here bounds something because there is a triangle. So this is a boundary cycle. This is a boundary cycle. Now this green cycle does not bound because this hole is there. It does. If this was filled up, then this cycle would have bounded something. So this green cycle, but look at this green cycle and this green cycle. The difference is this cycle here, but that bounds. And that is what, when we say that this green cycle is equivalent to this green cycle, are in the same class of this green cycle in homology. So that means these two green cycles are also equivalent to this cycles because their difference is a cycle which is a boundary. Like this and this one, the difference is this, which is a boundary. So again, a p-dimensional homology group consists of equivalent classes of cycles that are equivalent up to boundary. And what do we mean by this? I just tried to explain it. Okay, oh, by the way, so just to develop intuition, one-dimensional cycles, as we know, so two-dimensional cycles are something like surfaces. Think about that. So like think in 3 dimensions, you have a space, there are some voids, and those voids, the boundary of those voids are the two-dimensional cycles. Similarly, you can define 3-dimension and beyond. Okay. So let me now try to bring you to the world of topological persistence. Again, I'll be explaining it at a very high level, just to give you the intuition. So look at a set of points, the black points, which have been presumably sampled from these 2 curves here. Okay, we don't know the curve, only the samples are known to us. What one can do is the following. I can define a distance function in the plane with respect to this point cloud data. How do I define it? I have to define it at every point in the plane. So x is any point on the plane. I'm defining the distance function r of x as the distance of the point x to the point cloud P. What does it mean? It means the distance to the nearest point in the point cloud P. So for example, at this point, I have a distance function. Probably this is from this point, this is the distance. From here, I have this distance. So that is exactly the distance function R. Now, when you have a real valued function, I can talk about level sets or sub-level sets. What are sub-level sets? Is the set of points in the plane whose value are less than equal to A. This is the sub-level set R inverse 0A. Now, if you look at the sub-level sets, if you think about it, they are exactly, if you put the value A and take a ball around every point with the value, with the radius A, the union of those balls are exactly the sub-level set R inverse 0A. So this is the sub-level set I'm showing. Now, this is also a sub-level set for a different A. This is another sub-level set with an increased value of A. This is another sub-level set with even more, even larger value of A. So now, as I increase the value A, I grow the sub-level set space from this space to this space to this space to this space. And look at what is happening. What is happening at the beginning, I don't have anything right now capturing these 2 holes. But here it has appeared as 2 holes here. Here also these holes are there, but this hole has already disappeared. And this hole is still here. And maybe if I increase a little further, this hole will disappear. So this is exactly the concept of persistence. So this hole is persisting for a longer time than this hole. And there were some other holes which I'm not showing here, created, but they got destroyed very quickly. Those are due to noise. And the main property of the persistent is it captures the signal and dissociate the noise much earlier. So this is exactly what is called the persistence. So you can now put the algebra homology on top of it, which I am showing on the left side here. It's a sequence of space, as I said, sequence of space, then put homology group on this. That gives a sequence of homology spaces or the vector spaces called the persistence module. You do some kind of homological algebra here. You define what is called persistent homology. Let me not go into that detail. Now, let me illustrate the persistent homology in this picture. So this is a picture of growing simplicial complex. So simplicial complex, for example, the graph is a simplicial complex. It's one-dimensional simplicial complex. But when you throw in the triangles, then it becomes two-dimensional simplicial complex. I can throw in tetrahedra, it will become three-dimensional simplicial complex, and so on. So in this case, I'm showing a point cloud data, and slowly you are introducing more and more simplices, like the edges first. So now edges, more edges. Now some triangles has appeared. Maybe more triangles has appeared. And then there are some tetrahedra also. But remember, I'm just drawing the tetrahedra very flat in the plane. So I'm not talking about actual tetrahedra embedding. I can always talk about the tetrahedra embedded in a plane. They will intersect, but that's fine. For me, what is important to know that these 4 points are making a tetrahedra, and that is enough for homology computations. So now I have developed a sequence of simplicial complexes which are growing in terms of the simplices, meaning that every complex is a subcomplex of everybody else which are coming after. If you have such a sequence of simplicial complex, which is called a filtration, then if you consider the homology groups or simplicial homology groups of this sequence of simplicial complex, that gives you the persistence module. And from there, you can read something called the barcodes, like what I'm showing here. The barcodes are nothing but telling you how long an equivalence class in a homology group persists. Like in the picture previously, what I showed, how long this hole is persisting. The hole will be nothing but one-dimensional homology element, because it's a hole is a one-dimensional cycle, and they are captured by what is called the one-dimensional homology H1. So we'll be looking for when the holes are appearing as I'm growing, and when the holes are disappearing, like here. So this hole appeared, it stays, and then disappear, because some triangles came and filled them up. Okay, so then there is this notion of birth and death. The birth is when a class is born, like a class is born, like this one, most likely this one is for this. So this one got created some point here, then it persisted all the way up to here, because after this point here, it already got filled. So most likely it got, sorry, maybe this is the one. This is the birth point and this is the death point when it died. Similarly, you can see some other cycles also appeared and then died. And these are the bars. The bars tells you when a feature appears. Feature is a homological class, like this whole. When a feature appears, when does it disappear? Now, one interesting point is that a zero-dimensional homology actually captures what is called components, which we all know probably, the components in a graph. So for example, here are several components, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 components. So at this point, you will see, I'm sure there are 10 bars, this line will intersect 10 bars. So the components now, again, all the components with the vertices are born at the beginning, but then as the edges are appearing, they are joining components. That means the components are getting killed. The cycles, the zero-dimensional cycles are components. When you join two components, it becomes one component. That means one cycle is killed. And so that's what these bars are showing you, illustrating you. So exactly how the components are behaving are captured here. So at the end, only one component will remain, and that is exactly captured by this long bar, which goes to infinity. This is the bar for one-dimensional homology, and this is the bar for two-dimensional homology. This is hard to see in the plane, but actually, abstractly speaking, there are some voids created by maybe all the triangles of a tetrahedron is there, but the tetrahedron itself, the inside is not there. That will create a void, and that has probably happened here, created and quickly got killed. So this is called the barcodes, and you can compute it. There are efficient algorithms and efficient software for computing barcodes from a given filtration. So let me illustrate the power of persistent homology by illustrating how you can you can apply for, say, capturing clusters. So we all know the clustering problem. We have been given this, say, this 2-point cloud data. I'm supposed to capture, well, there is these two dominant clusters. Yeah, but you can do it with the persistent homology now, because I can talk about, as I just said, the zero-dimensional homology, I can say, and do, as I just illustrated, bring in the edges which are connecting the points in an increasing order of their lengths. So as they appear and appear, then you can talk about the barcodes, and you can see initially there will be all the small edges. There will be many bars which are all created, and they will quickly die because they will be joining together very fast. But then ultimately there is when this component is formed and this component is formed, they will stay for a long time, and ultimately these two will ultimately get joined only here. So there will be a little bit longer bar now here. And of course, there is this longest bar, which is the single component. But you can see there is this bar, which will tell you that it is longer than all the other noise. And this tells you there are two distinct clusters. Now, the point, now here is a fun fact with persistent homology. I could have not only done the H0, but I could have done also H1. I could have also studied how the one-dimensional cycles are forming as I am growing the filtration. In this case, what will happen, there will be cycles created, smalls created, but they will also quickly die. And that's why the H1, the barcode for one-dimensional persistent barcodes, they're very small. They are born, a lot of them are born, but they quickly die. So that means this is telling us that in this point cloud, there is no prominent one-dimensional cycles, but there are two clusters. However, my clusters could be this, and many traditional clustering algorithms will have difficulty to tell you that not only there are two clusters, but they are very cyclic. But persistent homology now can capture it, because I not only I have zero-dimensional homology bar, which tells me, as previously, there are two clusters, but also I have H1, where it will show there are two very prominent bars, because there are two one cycles, and that will be captured by these two bars in one-dimensional homology. Well, now, no method is a good method, at least for doing data analysis, if it is not robust to noise. I already told you or given you a hint that persistent homology is very robust to noise, because all the noise appears as a very small bars, which can be discarded. But to illustrate it, just to show you, here was one point cloud data. This is a little bit perturbed version of the same point cloud data. So there has been some noise now with respect to the blue point cloud, but they are very similar. Maybe they are sampling the same space, but with different measurements. But the persistent homology does capture it very well, because the two persistent diagrams are very similar. Okay, and you can not only, I can say it qualitatively, there is a quantitative proof and measurements how to really measure when we say something are very similar. I'll not go into that details. Okay, so rest of my time, let me devote it to some applications. But no way this is exhaustive. There are many applications which are appearing, particularly in image processing, computer vision, neuroscience, medical, molecular biology. I'm seeing more and more applications of topological data analysis in these spaces. I'll just give you some specimen of it. Mainly, I'm biased because I'm just giving you mostly in which I have worked. But by no means this is exhaustive. There are so many things are going on currently. Okay, but let me introduce you why the homology cycles are important and where do they appear. So, okay, let me show you this. This is a picture. Actually, I worked a lot in computer graphics some time back, and this is something we produced in one of our papers. But this is a very illustrative example. So here is the data which is coming from some CAT scan data of some brain aneurysm, if I remember it correctly. And then we reconstructed those features, okay, using some meshing methods. But then we are asked to detect where are the small holes, like here, or there is this necks, like here, and this necks around the cycles around the neck. And here the tunnels, the red ones, and you have to somehow localize it. You have to really tell not only there is this cycle, but what is the exact geometry of it. Okay, so these are captured by homology cycles, although geometry is absent in homology. But we brought the geometry into it using some other definitions, which probably I'll tell you in a moment. But just to illustrate where the cycles are important, particularly in this application of medical imaging or molecular biology. This is a picture from some molecule modeling. Also, in computer-aided design, those applications, people would like to see where the features are, like these tunnels. But whenever you say tunnel, it's a very vague word. What is a tunnel? We all know what it means by tunnel, but if I tell you, you quantify it mathematically, you will have a hard time, unless you take the refuse in topology. So here I'm just illustrating by tunnel, by features. I would like to detect this portion of these regions of these mechanical parts. Again, using these homology cycles, you can specify these particular regions. There are other applications in computer graphics for parameterizations. Let me not go into these details now. Okay, so let me, because this is something I already told you about the homology cycles, and hopefully I assume that you have some sense of what we mean by homology cycles. But as I told you, these are devoid of geometry so far, because topology does not require any geometry. You can define topology without any geometry. Of course, you can bring metric and can define a topology induced by the metric. That's what we usually do. But topology, you can define homology without any geometry, and that gives you the power, actually. That's why it is more robust, because it captures some global information without any local geometry. Okay, but now I want to bring geometry into topology, and that's what I want to do using computing optimal homology basis cycles. This optimality with respect to some kind of geometry. So I'll tell in a moment what we mean by optimality. Same thing, I can talk about optimal homology in a given space or given simplicial complex, or I can also talk about optimal persistence cycles in terms of the persistent homology. Okay, so let me go talk about the first one, optimal homology basis problem. Okay, so let me tell you here. So here, this is a double torus. The space of all one-dimensional cycles, okay, equivalent classes, can be represented with these 4 cycles, like here red, the one in magenta, yellow, and the blue. These 4 cycles, somehow their equivalent classes in the homology generate all cycles possible. You can generate, or said it another way, you can generate any cycle in this space, one-dimensional cycle, as a linear combination of these 4 cycles. This is called a basis. These 4 cycles are forming a basis for the one-dimensional homology group, because it can generate the entire space of one-dimensional cycles. Okay, but I'm not in, but see, if I give you, I'm interested in producing basis of this space, one-dimensional space, one-dimensional homology group. But if I give you these 4 cycles, although homologically or topologically it's the correct basis, you will not be satisfied. Rather than I would like to have these cycles to be detected. And there comes the notion of optimal homology cycles, which becomes the basis. So here the same colored 4 cycles, which is also a basis for one-dimensional homology cycles, but these are much more tighter. These are something which we like to compute. And this can be done with some algorithms. So first of all, for surface case, there was a beautiful algorithm given in 2005 in Soda. Then in general, beyond 1 dimension, it was proved to be NP hard, meaning that 2-dimensional homology groups, for the cycles for 2-dimensional homology groups, you cannot compute it optimally in polynomial time unless P is equal to NP. But the 1-dimensional problem was open, and that's what we solved in 2010, that you can compute the optimal homology basis for 1-dimensional homology groups in polynomial time. By optimality, now one can define the length of the cycle is the weight of the cycles, and you produce a set of basis cycles whose total length is the least among all possible basis cycles. That's the optimality. See, here I'm bringing the geometry because I'm talking about the length of the cycles, which is related to metric. Okay, so this is exactly the definition, and so we can prove that given a simplicial complex, K need not be surface, it could be arbitrary simplicial complex, you can compute an optimal basis, 1-dimensional basis, in order n to the power 4 time, where n is the size of a simplicial complex. By the way, later we have reduced this time to n to the power. Right now our best algorithm NQ. Actually, we wrote another paper and we realized this algorithm can be improved, although it becomes more complicated. Okay, so there is another version of this problem. The version of the problem is the localization. So the problem is the following. Suppose now, instead of computing a basis, suppose somebody has given you a cycle, a single cycle, like the red one here. And I would like to compute a cycle which is optimal in its class. Meaning that, remember I told you there are many cycles which form a class, a single class, because their difference is a boundary. So suppose I tell you compute the cycle which is optimal within this given class, that's called the optimal localization. So in this case, I would like to compute this. Given this, I would like to compute this. And this problem for surfaces, even for surfaces, it is NP hard actually. So this problem is harder than the optimal homology basis problem. Even it is NP hard for 1 dimension actually, for surfaces. But again, this is NP hard, this is a bad news, but there are some special cases we showed that you can compute the optimal homology localization problem for some special cases in polynomial time using linear programming. And that is the paper we had in 2010 in stock. Okay, now I come to my last topic on applications. I'll show some other applications also, but this is the more topical, is that now I'll be interested in computing cycles, optimal cycles, which persist. So far, I did not talk about persistence when I was talking about the optimal cycles. So what do we mean by this? I mean the following. Again, I illustrate with a picture. Suppose you have been given this point cloud data, and you have formed a filtration using some simplicial filtration. You put some edges, then triangles. So you build this. I already showed you how to build this, and there are several mechanisms how to do it. I'll not go into that details. So for example, from this, I have built this filtration right now. Maybe at this point, there are some edges, maybe there are some triangles I'm not showing, but there's some edges. So now if you do this, then you get these barcodes, remember? You get these bars of the persistent homology, so 1-dimensional homology. But then I ask you, given this bar, I told you for each bar, actually there is a equivalent class which is born here. 1-dimensional cycles, a class of cycles get born, and that class of cycles get destroyed. But I ask you, give me the cycle within this class which is optimal. So it's something like the localization problem, but I'm asking in the context of persistence now. And this we showed for 1 cycles, you can solve it. You can solve it for 1 cycles with polynomial time. Okay, and this is actually we implemented the software. This is the output of that software. For on this one, exactly it has at this point for these 3 bars, I'm showing these 3 cycles. These are the optimal ones for these 3 bars. Of course, for each bar you can compute. So for each bar, it will tell you where somehow now so if you look into this barcode, it somehow you don't get the geometry where the barcodes are in terms of the actual space. It gives you a signature from the space, you get a signature, but you can somehow there is no relation of the bar in terms of the geometry here. But now we can tell you, well, this bar corresponds to this optimal cycle here, which is going to persist. So somehow this is bringing the geometry and topology are again brought into one thing through this mechanism in the context of persistence. Okay, here again we are applying it to some disease eye data. So you can, this is an image. So you can always view an image as a function defined on the plane. You take the pixel values as the function values, and then again you can talk about the sublevel set filtration of this function, and you can talk about the barcodes, and that's what we have computed. And again I can talk about for this barcode the longest bar, because that is probably something prominent feature. With respect to this feature, tell me what is the optimal cycle, and this is giving you this cycle here. For this one, this is giving you this cycle. For this one here, this is you this cycle. So from the barcode, now we can have a mechanism to go back to the space and somehow see where the features are which are persisting for a while. Okay, now this particular concept of computing optimal persistence cycle actually is a very late result, very recent result. In 2020 in SODA with my students, you can check, we produced a polynomial time algorithm that we gave an order n squared time algorithm for computing optimal persistence cycles for each barcode for the case where the space is pseudo manifolds. By the way, we proved that in general the problem is NP hard. This computing optimal persistence cycle in general is NP hard. But again, there are some specific cases which we call the pseudo manifolds, which are very important actually from the application point of view. Pseudo manifolds are, for example, the triangulations in R3 are pseudo manifolds. So you can apply this algorithm for triangulations in R3, R2, for example. So we showed that there is a polynomial time algorithm for computing optimal persistence cycles. And this has been also implemented. Okay, so again, now I'm going to show some examples of our applications. We applied our persistence cycle, optimal persistence cycle methodology for some data sets in biology. So here I'm showing some nerve data. We again, so when I say top 20, it means the top 20 barcodes in terms of the barcode length. So corresponding to those top 20 barcodes, I'm showing the cycles here. Then if you increase the top 300, there are many barcodes. Top 350, it shows where the cycles are. And you can see it does capture the features which you will try to capture in such an image. Here, the same thing we have applied to some image for Drosophila larvae. Here we applied our algorithm, the more generalized algorithm for 3D data. So in 3D data, we are looking for two-dimensional optimal cycles. So again, I told you two-dimensional optimal cycles are something like voids. Is like a surface. So again, you can compute those voids which are persisting much longer time, like they are more prominent than others using this methodology. And here I'm showing this data set on something called cosmology data. So cosmology data is a density data in 3 dimensions. It captures the density of dark matter in our universe. And here, actually, I'm showing only a sector of our universe. and when we apply it, it just captures the concentration of the dark matters in the universe. So this is the top concentration at this. Then this one is the second concentration we find. So when I say top, second, third, this is with respect to the length of the barcodes. So each barcode the length tells me how prominent. So the previous one was the most prominent because it persisted the most. Then this one is the persisted most. Then this is the third, fourth, and we went up to fourth. Then here is another data set on the hurricane data, Isabel Hurricane data. I don't know, some of you may remember the Isabel Hurricane. It was a devastating hurricane some time back. And for this data set, again, we have the function value as from R3 to the pressure. We took the pressure as the real valued function defined on a three-dimensional data set. And then we talked about what is the prominent two-dimensional homology cycles. And it captured, for example, this cycle here. I'm just showing here. This is the eye, and this part, this is the region it identified. And apparently, this is consistent with what actually the meteorologists will identify most pressure zone, or the where the storm is most furious. Well, this is again applying the same methodology, but this time I take the function as the velocity of the wind. So this one was the pressure. This is for the velocity of the wind. Okay, so now I come just tell you another applications of topological data analysis. This time it is applied on road network detection. So you know this GPS trajectory data. So here, for example, on the Berlin road network, this is the some GPS trajectory. So the blue data is the GPS trajectory data. So again, you can see if the car is going over a road, most likely that will be traversed so much, you will have a high density data here, and these holes and these ones will tell that there are no roads there because no car travel there. So from such a data, one would like to somehow reconstruct the road network of Berlin, and that's what we can do using something called Morse theory. And here I'm showing the output of our methodology in the black. So from the blue data, we reconstructed the road network using our topological method. Again, this is a little bit completely different from what I showed you previously. That this is another thing about the topological data analysis. Right now, topological data analysis is really flourishing in various directions, and this is another direction where the Morse theory is playing a tremendous role, because the Morse theory in mathematics is very well defined, very well studied from the smooth perspective. But not recently, couple of decades back, maybe in 90s, one mathematician called Robin Forman, actually he invented a discrete version of this Morse theory called the discrete Morse theory. And that turns out to be very useful now for applications. So this is another thing I realized, or at least I find is useful. In mathematics, there are many concepts which are developed from a smooth perspective, but we who are working on data analysis from computational viewpoint, somehow we need to discretize those notions sometimes. There are two approaches. You can always approximate with discretization, the smooth case, or you can develop a new theory on the discrete version completely. And this is the second approach. And often the second approach is, in my opinion, much better, because you can directly now argue about your correctness, and you can see what algorithm is the right one to go for. And this is a very good example of what we did using the discrete Morse theory. How do we compute this road networks? And actually, what I don't have much time here left. Okay, let me not explain what it is. This is again using the same methodology we worked on the road network, but this time the input is not GPS trajectory. Input is a satellite image. So it's a different image, a different input. Here we combine a little bit of machine learning with topological data analysis, our method, together to come up with this reconstruction. Here is another applications to material science. So this is something we are working right now. So material science, again, it's mainly on image, working on images, but then again, in the context of material science, problem becomes a little different. So here I'm showing you some data, the images of microstructures. So sometimes in materials, there are some microstructures which actually determine the property of the materials. The material scientists are very much, they want to really study these microstructures in the materials. So here I'm showing a polymer data on the left. There are these microstructures. On the right, actually, this is the microstructure on a lithium-ion battery. The performance of the battery depends on these microstructures. And we are trying to detect, using one of our methods, this microstructure effectively, where you couple the domain knowledge, the material science knowledge, with the topological data analysis, so that your detection is effective. Again, here is another applications we did for protein classifications. And protein classifications, in this application, what we did, we applied our topological data analysis. These features we combined with other features, and we applied the neural network pipeline. So what we did, we infused our topological signatures into the feature vector of the neural network pipeline, and we see that it gives a better result. Okay, I'm almost done. Let me conclude that why am I advertising topology and geometry? The advantage of topology over geometry, when I say and, one should not forget geometry, but I'm saying that topology gives you sometimes better things. So because it is global, robust, sometimes it is easier. There could be many applications possible, as I'm just doing it here. So let me acknowledge all my students. I have, over the past 25 years, I have so many students helping. All these works, the credit goes to most of the students, postdocs, and I have quite a few collaborators over different institutions. And definitely without their knowledge and help, all this work would not have been possible. And then of course, I acknowledge the support of NSF, AFRL, and the recent tripods, which we got in Ohio State University. Thank you very much. Just to tell you, just to finish, we are writing a book. Actually, I'm writing a book, almost it is done, on topological data analysis with my colleague, Yusu Wang. But the emphasis will be, we try to give the emphasis on algorithms, because there have been some topological data analysis book available. They emphasize more on mathematics. Definitely, we cannot do without mathematics, but this time the book is gives a more emphasis on algorithms from computer science point of view. Hopefully, this will appear sometime next year. Thank you. And some of the materials will be there in this course, which I'm showing here. Thank you very much.
Thank you. I appreciate your talk. I think we have some minutes for questions. So if folks can either type the question on the chat or use the microphone.
Please ask over microphone.
Yep.
Can I just ask a quick question about just to get some intuition? In the example, you have two circles, and you use the barcode, and then your two circles are separate. Yeah. But in clustering, typically people look at examples in which one circle is inside another circle.
Oh, that is not a problem.
Yeah, if that's the case, what would the barcode look like?
Oh, same. So again, that is the beauty of topology, because it is oblivious to the geometry where you put the site, at least in this example. So I don't know, I cannot draw. Can I draw? Let me see if I can. Okay. So I can draw. Okay, can you see my drawing?
Yep.
Okay, so suppose you have these two cycles here, and then you have the point cloud data in these cycles and these cycles. The barcode will give you this two long bars. It does not matter whether this is the case or this is the case. It doesn't matter.
How about if the two circles intersect? Then that will be different, right?
Yes. Okay. If the two circles are intersect, but see, the problem here, if you don't know, even can you tell me whether there are 2 cycles or 3 cycles? I may argue that there are 3 cycles.
Yeah.
So in this case, what will happen? I can tell you, you will get one cycle, this one, another cycle, this one, and this one. You will get 3 bars in these cycles. Yeah, but these are very good questions. Thank you.
Thank you.
Questions? We probably have time for one other question.
May I ask a question?
Sure, of course.
Yes, I thank you for your great works. But by the way, is it also possible for you to regenerate some samples, like a generative model that exists in machine learning? Is it possible for you to do that with your topological approach?
Ah. Yes, this is a very good question. So right now, I don't know how to answer it. People are working on it. So as I know right now, you need some more techniques, but there are some possibilities, maybe. It's a very open question, actually. You ask how to do, for example, GNN, right? Probably that's your
Yeah, exactly.
Yes, yes.
Yeah.
Okay, so as we speak, we have started working in it, and now we are seeing slowly what can be done or what cannot be done. It's an open question, I must say, but I see a great possibility.
May I ask why you see a great possibility? Because for me, like I admire topology, even though I'm very bad at it and I don't understand it quite well, but I admire it. But the problem for me with the topology is that even though it's a robust in terms of a very important global topological features, but sometimes when we want to have some more ideas about confidence interval or some kind of hypothesis testing, like I find that I mean, probably it's because I don't know any about it, but still, like I don't quite see how those ideas can become more tangible, because it seems like they're too free for me. Why would you see more possibilities? Like, is there some kind of a section of a topology that you think that is particularly promising in terms of that kind of generation?
Yeah, maybe I give you very high level answer why I said it, because in a generative model, what you would like to do, given some sample from some space, I would like to generate more samples from given a graph. I would like to generate graphs which are of similar type, right?
Yes.
Right. So, but see, the power of topology will be if I can do a topological features on the graph, then I will use those topological features to generate those graphs. So they will be most likely very similar. That's why I said there is a possibility.
Yes, thank you.
Thank you.
Thank you, everybody, and thank you, Tamal, for giving this talk and for visiting with us today. I really hope that we could have you here in person in not so distant future, so that we can do other activities like going out and showing you some lunch and dinner venues that we have in Saiba. Thanks again. Look forward to talking with you. And I will be in touch to request another meeting of a one-on-one meeting between our people and you. Thank you.
Yeah, sure. Thank you.
Everybody.
Thank you very much. All of you.
Bye now.
Bye.